Okay, what I'm going to talk about now is some more Gibbs free energy stuff. And if I have this chemical equation and I look up the Gibbs free energy of formation of each one of these, I'm going to have for NO gas, the Gibbs free energy formation is 86.6. The free energy formation of oxygen gas is going to be 0. And the free energy formation of NO2 gas is going to be 51.0. This is all in kilojoules per mole. I didn't want to write the units 3 times. The Gibbs free energy of formation is just like the enthalpy of formation in Chem 1A. It's the Gibbs free energy of forming 1 mole of this from its elements. And this little circle here means the Gibbs free energy of formation of this under standard conditions. That's what the circle means. This means, the circle means the Gibbs free energy of formation of this under standard conditions. And it means, the little circle means the Gibbs free energy of formation of this under standard conditions. Again, what are standard conditions? They're a scientific standard, a standard that scientists have chosen that mean standard conditions means if you have a gas under standard conditions, it means it's the pure gas at 1 atmosphere of pressure. Any particular temperature is not what's relevant for standard conditions. If it is a solid, it is the pure solid at 1 atmosphere of pressure, but pressures don't really affect solids. Okay? And the if you have a liquid, well, liquid or solid, it's the pure liquid or pure solid at 1 atmosphere of pressure. And if you have something that is aqueous, it means, like if I had HCl, aqueous, under standard conditions, it means 1 molarity hydrochloric acid. So if I have standard conditions of anything and it's got AQ or aqueous, it means everything there is under 1 molarity condition. Here, this means if I have the Gibbs free energy of formation of this under standard conditions, I found the energy needed to form NO from the elements nitrogen and oxygen. And I did it when the nitrogen and oxygen were under standard conditions, meaning 1 atmosphere of pressure each. If I want to calculate the Gibbs free energy of reaction for this, just like we did last time with the previous problems, the Gibbs free energy of the reaction is going to be products minus reactants. I have 1 mole of this, so it's going to be 1 mole of that times 51.0 kilojoules per mole. So you see how the per moles are going to cancel out. Minus 1 mole of this times 86.6 kilojoules per mole. Plus, don't forget the minus sign in front of the bracket here, plus a 1/2 mole of this, and that happens to be 0 kilojoules per mole. And so what I'm going to end up with is going to be 51 minus 86.6, 51 minus 86.6, and that's going to give me minus 35.6 kilojoules. Okay, and if I wanted to figure out what the equilibrium constant expression for this was, I would remember that's equal to minus RT natural log of K, and R is the gas constant, T is temperature. I have to know what temperature I'm running the reaction at, and K would be the equilibrium constant, and I would solve for the equilibrium constant. The next thing I want to talk about is what if this reaction is not run under standard conditions? For example, a lot of chemical plants, they're not going to run the chemical reactions under standard condition, they'll have all the gases at 1 atmosphere of pressure or something. They might have them at several hundred atmospheres of pressure. So if I wanted to know what the Gibbs free energy of this was under non-standard conditions, I need an equation for that. And the equation I'm going to give you, I'm just going to drop it down out of the sky. I'm not going to prove it to you. Some equations I prove to you, some I don't. The Gibbs free energy for non-standard conditions, this is not formation, excuse me, that's reaction, is going to be equal to, this is for the reaction, it's going to be equal to the Gibbs free energy of the reaction under standard conditions plus RT natural log of Q. It has to be natural log, not LOG log, because this is base 10, this is base E. So they're different. So if I want to know what the Gibbs free energy for this reaction is under non-standard conditions, I'm going to find out what its Gibbs free energy is under standard conditions. I would do it this way. Plus I have this term that adjusts for the non-standard part. So let's say I wanted to know the Gibbs free energy for this reaction when the partial pressure of NO2 is, let's say, 100 atmospheres. The partial pressure of the O2 is 50 atmospheres. And the partial pressure of the NO is, let's say, 25 atmospheres. Those are clearly non-standard conditions, right? And let's say this is at temperature equals, let's say, 298 Kelvin. Okay? Well, to calculate the Gibbs free energy under these non-standard conditions, I'm going to have delta G of the reaction under non-standard conditions will be the Gibbs free energy under standard conditions, which we just calculated, minus 35.6 kilojoules per mole, plus RT, natural log of Q. R, since we're talking in terms of energy, R is going to be 8.314 joules per mole Kelvin. Temperature will be 298 Kelvin, because that's the temperature I chose to make a problem. Natural log, and Q is the reaction quotient. Remember, we talked about that before. And it's going to be products over reactants. So it's going to be the partial pressure of the NO2 to the 1 power times the partial pressure of the NO to the 1 power times the partial pressure of the O2 to the 1/2 power. And then notice this is kilojoules, and that is in joules. If I'm not careful, I'll mess up my units. So this is what I'm going to do. If I divide that by 1,000 to turn it into kilojoules, that would be 8.314 times 10 to the minus 3rd kilojoules per mole Kelvin. A lot of times when I have to convert it into kilojoules so it's consistent with this, I just remember if I divide by 1,000, that's the same as 8.314 times 10 to the minus 3. Okay? Okay, be quiet. Okay? So I'm going to go ahead. I'm going to erase this. I'm going to plug these numbers in here. These numbers I just picked to make a problem. So here I'm going to have 100 atmospheres. Remember, reaction quotients and equilibrium constants don't have units. Partial pressure of the NO is going to be 25. And the partial pressure of the O2 was 50, but that's to the 1/2 power. So I'm going to get minus 35.6 kilojoules per mole. And then 8.314 times 10 to the minus third times 298. I'm going to have plus 2.48 kilojoules per mole. Oh, excuse me, Kelvins canceled, moles didn't. Natural log, and I'm going to do this, I just want to do this part separate. So we're going to go 100 divided by 50 squared, not squared, square root of, 100 divided by 50 square root of, divided by 25. That's going to give me natural log 0.566. Right? Pretty much that. So I'm going to take the natural log of that times 2.48, and that's going to give me negative 35.6 kilojoules per mole minus 1.41 kilojoules per mole. You see, it'd be very similar, not exactly the same, and my birds just really want to talk right now. Minus 35.6. And that's going to give me negative 37 kilojoules per mole. That's the Gibbs free energy under non-standard conditions. Okay? Where did this come from? I just dropped it down out of the sky. Okay? It is derived, but some equations I'll make you guys know the derivation. Like, for example, the Gibbs free energy itself, right, from the second law of thermodynamics, entropy. And here I'm just dropping this one down out of the sky on top of you. Okay, let's try another one, just for you guys to get the feel for it. By the way, that tells me under non-standard conditions, it'll be spontaneous. And the max amount of work I can get out of it would be 37 kilojoules per mole. That's what that means. Suppose I have this reaction here, CH4 plus 2O2. Oh, this is the phases really mattered. 2O2 makes CO2 plus H2O, and in this case it's going to be in the gas phase, not the liquid phase. And earlier I did this in a previous video, and I calculated the Gibbs free energy for this reaction was equal to negative 817 kilojoules per mole. 817, not 8.7. That means the minus sign means it's spontaneous. The 817 kilojoules per mole means if I react 1 mole of this chemical reaction, the maximum amount of work I could get out of this would be 817 kilojoules per mole of this in the reaction. Okay, I'm never going to get quite that much because no engine's perfectly efficient, but you guys get the idea. Suppose now I want to know the Gibbs free energy. By the way, that's under standard conditions. That circle means standard conditions. That means I ran this CH4 plus 2O2 makes CO2 plus 2H2O. That means in this container, this was at 1 atmosphere of pressure. The O2 is at 1 atmosphere of pressure. That's at 1 atmosphere of pressure. And that's at 1 atmosphere of pressure. Since we're talking gases, that's standard conditions. What if I want to calculate the Gibbs free energy when the partial pressure of the methane is, let's say, 1,000 atmospheres. Let's make that 4 sig figs. The partial pressure of the O2 is, let's say, 500 atmospheres. The partial pressure of the CO2 is, let's say, 5 atmospheres, quite a difference. And again, I'm just making up numbers to create a problem. And the partial pressure of the water is, let's say, also 5 atmospheres. Okay? That means I have a whole lot of reactant and not much product. My intuition says it's going to want to go this way, right? Because I got a huge amount of this and not much that. That's my intuition, but intuition is not nearly as good as a calculated number. So the Gibbs free energy of this reaction will be equal to the standard Gibbs free energy of the reaction plus RT, natural log of Q. I didn't specify a temperature. Let's say the temperature is 825 Kelvin, just to pick a number. Okay? This will be equal to minus 817 kilojoules per mole plus 8.314 times 10 to the minus 3 kilojoules per mole Kelvin times 825 Kelvin. Sloppy writing there. But you guys know that already about me. Times the natural log of the partial pressure of the CO2 times partial pressure of the water squared over the partial pressure of the methane times the partial pressure of the O2 squared. Right? So, what can I erase? Well, I guess I'll just have to erase this piece. Okay, so delta G of the reaction is going to be negative 817 kilojoules per mole plus 8.314 times 10 to the negative third times 825. It's going to be plus 6.86 kilojoules per mole. Natural log. What's the CO2 concentration? 5 atmospheres. 5.00, excuse me. Times 5.00. And that's water, that's squared. Divided by the methane. 1,000 atmospheres. And the O2, which was 500 atmospheres squared. So I can go ahead now and erase the bottom pieces. So 5 times 5 times 5, 125, divided by 1,000, divided by 500 squared. That's going to give me delta G of the reaction. It's equal to negative 817 kilojoules per mole plus 6.86 kilojoules per mole, natural log, and here I have 0.123456 and a 5. 0, 0. So I take the natural log of that times 6.86, and I'm going to get negative 817. Can't write today. Kilojoules per mole minus 99.5 kilojoules per mole. And I get negative 917 kilojoules per mole under these non-standard conditions. This tells me, number one, that it's spontaneous. Number two, I'll get a maximum of 917 kilojoules per mole of this reacted that I could use for useful work. Also, it tells me under these non-standard conditions, I'll get more energy out of it under non-standard conditions than I will under standard conditions. Under standard conditions, where everything's 1 atmosphere, I get 817, right? And under these non-standard conditions, I get almost 100 kilojoules more. Okay? So that's pretty much how you guys do that stuff. Next time, when we get into electrochemistry, we're going to use this and the fact that Gibbs free energy is equal to minus NFE, and Gibbs free energy under standard conditions is equal to minus NFE naught, where this is voltage, F is the Faraday constant, and N is the number of moles of electrons that are transferred in the redox reaction. We're going to end up with E of an electrochemical cell is equal to E naught of an electrochemical cell minus 0.592 volts over N log Q. I hope I remember the 0.592 volts over log Q, and that's the base 10 log. We'll see what, wait a minute, if I have natural log here, how do I get base 10 log here? So we're going to do this, and I hope I remembered the 0.592 correctly. But we're going to use this. This is called the Nernst equation. And this is voltage, like you would measure with a voltmeter, comes from the Gibbs free energy, and the Gibbs free energy, remember, comes from the second law of thermodynamics. So this comes from here, and that comes from there. Okay, we'll go over that next time and do some calculations with it. If you guys have any questions, you guys know to come to office hours or email.